Okay, welcome back. We had one last question on homework 3, kind of working through. This one is looking at like a mass on an incline with a spring attached to it. So in this case, we want both the equation of motion and we want to find the solution to it. So if we know its initial position, we know its initial velocity, what does the motion look like? And that's the question that we're trying to figure out here. So at first, for the general equation of motion, or in the free body diagram, we want to look at like what happens with friction, and then the actual solution that we look at, we'll simplify it and say like, for one case where friction is 0, what is the solution to that equation of motion? So again, back to forces causing motion, and then equation of motion based on those forces. Cool? What do you think? Where do we start? Free body diagram, yeah. It's the broken record, the Professor Cooper. Every day, you come in, ask you what should you do first. It's always free body diagram. Once in a while it might be like kinematics, of like solve the kinematics first, but even there, you can always start with a free body diagram. Yeah, so let's start there. What does it look like? What do you think? Definitely not static. Yeah, this thing's gonna be like bouncing all over the place.
But like in the free body diagram, you know a mixture. If the spring is pushing your whole.
Yeah. Does it matter? Yeah, yeah. Is it going to change? Yeah. So the direction of motion, so we need something that's based on direction of motion. For the spring. I'll draw what I have so far. Or at least what I've seen so far. myself a little more room. All right, so far there hasn't been any real discussion about gravity. Most people have said like it's going to act down. That makes sense to me. Normal force has to be normal to the surface, to like the actual plane that we're on. And again, no real issues there. Spring force, this one, some people drew it immediately this way, but then started to ask like, oh, what happens when it bounces back? Do I need a new spring force there? And then friction, I saw some people draw it this way. But again, then some people were thinking about it more, erased it, and had like no friction force, of like weren't sure where to go. So what do we think? Where, for the spring force, is it okay to draw it up and to the left? So if we have positive, if we're moving positive velocity, spring is stretching backwards.
If you're going down, the spring is stretching and thus pulling back.
Okay.
Also, moving down, of course, the against direction early on.
So let's say spring is compressed and we start to move down.
Start to move down, then force.
Is the force pulling us back?
No, it's pushing you forward.
Still pushing. Until you slow down?
Yeah, when you start going back, first you start moving out first with spring.
So what's the main first spring? What is the spring force? How does it work? How do you get more force out of a spring?
You either stretch it or compress it more.
Stretch it,
This is based on
compress it. So based on like position, right? Like how far we are along here. So if that's my y, this is my x. There's some like unstretched, like if the spring is in its unstretched position, it has no force. No positive or negative. So I think force of the spring should point up this way. And that's just, I'm gonna just say that it's always pointing up that way. Why is that okay? Yeah. How would it become a negative force? Negative displacement. Yeah, so anytime displacement's negative, like if our delta x term is a negative delta x, then we have a negative force, but the negative is now a positive, like, compression force. So here is like that k delta x, or like x minus L0. So it's open. And the main thing that I'm doing here is I'm using my reference frame and saying, if I have a positive force, which direction is my spring force pulling me? And in this case, it's pulling me back to x equals L0. And that's okay. How about force of friction? What about for this one? Does this have some, does it depend on position?
No, it depends on the motion,
Direction of motion? Does it depend on how fast you move?
No, not like that.
Not really? I mean, kind of, because if you're not moving, then there's static coefficient, but if you are moving, there's a dynamic coefficient. But that one's kind of a step change, right? Like if you're moving, you get one value. All right, so what are we gonna do with that one? because it's attached to a spring, and the spring is definitely going to bounce up and down. Sooner or later, friction will stop us, but at least to start, it's going to keep moving us. I'm going to use my same argument and say friction pointing this way is correct. And just, if I'm moving forward, friction should be pulling me backward. Does that make sense?
Yeah.
And then I need something to change the direction of friction in my equation. And we'll come back to that, to this one. We'll just call it like question mark for now. What did MA look like? What's our mass times acceleration?
Based on that drawing, it's in the direction of the slope.
In that slope? Yeah. So again, I drew a coordinate system where x is the slope. So I only need to consider motion along that slope. So I can call this one, I'll call it mx double dot, like acceleration along my x-axis. You can call it max or ma, or we only have one value of a, right? So for now, you can just plug in a like FF, like whatever you labeled friction as, let's just plug that in for now, and then we'll figure out how we can deal with it afterwards. So that's our next step. We want, what is MA in terms of the applied forces that we have? We have a free body diagram, we have our MA term, so which one of these are moving along that MA term? Which ones are causing motion up and down? Like normal force is normal to the motion, so that one definitely doesn't cause changes in motion. At least in this case, because all of our motion is always 90 degrees to it. But then there's other forces that are right parallel to those, some that are Again, really that's what the free body diagram is telling us. They're asking modes and y components. Yeah. And they all have to add up to our MA components. Okay. Zero, if the slope is zero, right? Here we go. Here we go. What did you do for friction? How did you deal with it?
Well, looking at it, I assume that at first it's going to start moving down.
Okay.
Because the force of gravity is I just said force of gravity is going to be going this way, making it negative.
Okay.
Along with the force of the spring. Really the only thing that's going down is the force of gravity.
Okay.
That's now what I assume that model.
So what if it started as a stretched string and pulled up?
Then flip the force of gravity.
Then that should, you need a whole new set of equations.
Think so. Or you could probably just edit it a little bit to
Okay. What would you edit?
going down, I think this is positive, correct? So that is positive.
Okay.
Would be positive as well. Yeah, what does that mean? Yeah.
So that's where like it's extract, stop, direction, but
Yeah, so like if you have a positive velocity, the sign of, say it's moving down at 10 meters per second, the sign of x is as my g or not is but if you're moving up at 5, like -5 meters per second, the sign of x is negative. So it only ever gives you -1. Another way that I usually write it is velocity divided by absolute value of velocity. The ratio is always, the magnitude is always 1. The ratio is either positive or negative.
alright, so that's not really a part of the equation. This is just your results of our.
Yeah, but it's part of the equation because you need something to say.
Oh,
You need others. Yeah. So if you're solving it by hand, you can always relate, but you have to solve for all the positive velocities and then all the negative and all the positive. Yeah, I mean, it's fine. It's not the end of the world, but it just takes some focus.
We have mg sine theta, at least that's what I saw most people write. Any issues so far? No? Minus our k delta x for that spring force, and then minus that force of friction.
Force of friction equals a normal force times the rate of friction. So equal the component of the force of gravity at an angle times
Okay.
which is mu naught mg cosine theta.
Any issues with this substitution? Force of friction is a mu times mg cosine. Yeah.
Well, then that wouldn't change its direction.
It does not change direction.
Always be pointing up the slope.
Yeah.
So if we start, once it switches and starts moving up the slope due to the spring force, it'll still be pushing that way even though
Yeah.
experimentally it'll be going down the slope.
Yeah, and so this is something that's a little weird about friction, and it's usually why people don't deal with friction is because it keeps changing directions. And even though it's a constant force, so it is a constant force, but if you change directions, then it's the same constant force but opposite direction. So the magnitude, the sign of it changes. So I did see this multiplied by SGN of x dot. Saw that on a few. Well, what would this do?
Once we define the direction of motion is positive or negative, multiplied by that direction, by that sign of the motion.
Yeah. Then it would fix it. What is this? Have you seen this function before? Like SIGN or SGN, anything like that? It's kind of a weird way to write it. What about this one? Like V over absolute value of V.
Yes.
What would that do? For unit vectors? Yeah, okay. what is V if I'm moving, let's say 5 meters per second down the ramp? What is 5 divided by 5? 1, okay. Let's say I'm moving -3. I'm moving up the ramp at 3 meters per second. -1. So that SGN value is just another way. Usually I see it written as like V over absolute value. So you get the direction, but not the magnitude. And it's not changing the value of your actual like force. Yeah, it just flips from positive to negative depending on are we moving forward or backward. So if we're moving forward, we have a negative force. And when we're moving backwards, we have a positive force, negative, negative. Cool. All right, that's our equation of motion. Well, I mean, we could do some extra stuff, right? Just get rid of that mass term, so now we just have like the actual motion equation. Like what is acceleration in terms of, here we have constant, we have an x term, and we have x dot, like a velocity term. So our acceleration is a function of time, kind of. I mean, our forcing function is a constant force. We have position and we have velocity. So as those things change, our acceleration's changing. What? I think that's part A. We're done. All right, part B. Let's give ourselves like an actual value of like 1 meter, 2 meter per second. What do we want to do? Say this is 4 Newton per meter. Just so we can plug in some numbers, and then we can. Oh yeah, and then we also have mu is 0. Kind of like this. 4 Newton per meter over 1 kilogram. And then also minus 0 times g cosine theta. How do we solve this problem? Some people are in or have taken like differential equations. Have you done like second order differential equations? Some? Yeah. What did you do with second order differential equations? Okay, yeah, is that what you call it, general and conditional? Oh, okay. So I've seen like homogeneous and particular. Does that sound familiar? Okay, all right, good. I never know if there's like, I don't know, kids these days, like, yo, he's so out of whack, Professor Cooper. We call him, I don't know, we call them millennial equations and Gen Zers or something. Like, I don't know. It's just what they called it when I was in school. Homogeneous and particular. How does that help if I have, like, x is now 2 functions of x? Doesn't it just make more equations, more work? More equations, more problems. It is more problems, but maybe it's easier problems? Maybe? Yeah, we'll do that. So if I take 2 derivatives of x, it's the same as taking 2 derivatives of both of those homogeneous and particular solutions. Maybe we should write that, H. Homogeneous XP particular. Kind of like that. So we have homogeneous, we have particular. Then I'm going to plug them. I'm just going to take these definitions and plug it right into my differential equation that I have. I'm not doing anything right now. I'm just saying, like, I'm going to solve multiple problems by just plugging in stuff into something I already know. So x double dot h plus x double dot p is g sine theta minus 4 over, I'll just call it 4, minus 4 x double dot h plus, no, not a double dot, it's just x h and the xp. I just like putting dots on things. Again, haven't really done anything, and I'm kind of walking through this because, like, this is not a differential equations class, but it is really helpful to see, like, what can you do with these like equations of motion from here. So this is one way to kind of go about solving these problems. All right, I wrote out my full equation. I'm going to split it up into 2 equations, and the 2 equations are now going to be a little easier for me to solve. I've seen them hundreds of times. Maybe you've seen them like a couple of times in your life, and now you'll see them again. So sooner or later, you'll see them hundreds of times. It catches up with you. Oh wait, then minus 4 xp, like that. All right, there's equation 1, there's equation 2. Why did I put the g sine theta in equation 2? What does that help me do with equation 1? Yeah. Or either or, yeah. Or any y's. It's just like, okay, yeah. So now in that second equation, I could start looking at it as like, what's constant? Like, what are the, and that's why we call it like homogeneous and particular. The homogeneous is sort of like what happens to this system when all the other constant forces are gone. Like, it's just a spring that's bouncing. And then the second part, the particular, is like, if there's a constant force, how does that change the solution? What's particular to this forcing function? All right, so I'm gonna start with the first one. What function, if I take two derivatives of it, it's the same function, but times a constant, times a negative constant. Cosine or sine, just to be safe. Let's throw both of them in there. Why not? Sorry? So I said, what function can you take two derivatives of itself, and you end up with the same function but times a constant? Sine and cosine. Okay. Yeah, because if you have sine and you take a derivative, if you have cosine, take another derivative, you end up with negative sine. And if there's something inside, like a sine of 2t, then you have 2 cosine t, and then negative 4 sine t, which is kind of what we have here, right? So it's got to be something sine omega t plus something cosine omega t. And it could be either, it could be both, it could be one it could be one or the other, or it could be a combination of both. So throw them both in there and we'll figure it out later. What did I do right there? Magic? I'm a math magician. Take two derivatives, so I end up with like that negative omega squared. I pulled it out, and I did that because this is xh, and this is xh, our homogeneous x term. So this is xh, and this is negative omega squared xh, which is exactly the equation that we have above. What is omega? 2, okay, 2 is good. Okay, now like philosophically, what is omega? What is that thing? Yeah, root k over m. What is that? It does give us an angular velocity. So units are going to be radians per second, like a unitless distance per distance over time. Yeah. Frequency. What kind of frequency? But there's no angle changing, right? It's not like the slope is changing. Sorry? Spring, yeah, it has to do with the spring. The spring oscillating. Yeah. The period, okay. Periods get also amplitude. Actually, so it won't be the amplitude. Amplitude's gonna have to do, it'll do a combination of like A and B. Like that'll set our amplitude. Like if we had 10 cosine, then we have an amplitude of 10 meters. Yeah. Resonant, it could be the resonant frequency, and then the other term for it is like, so resonant and natural frequency are both usually interchangeable, but natural frequency is kind of like, for this unforced system, it's going to oscillate at this natural frequency. The only difference for so if you have an undamped system, then resonant frequency is natural frequency. As you add damping, there's damped frequency that's a little bit different, just usually within like 10% of your natural frequency. But that would be your like resonant frequency of like where it's going to oscillate. But that's our natural frequency. So that's all we really did there in equation 1 was solve for natural frequency. So we know, and we know the form of like what is the time varying form. What do we want? G sine theta. Oh yeah, this one's 4. How do we solve this equation? The second derivative is equal to a constant minus 4 times the function. I'll tell you a secret. The best way to do it is just guess. So start off with like the simplest guess we can have. Super boring guess is that it's 0. Just that it's not going to change. But then we have 0 equals G sine theta minus 0. Does G sine theta equal 0? No, so that one's no good. What if it's a constant? I should use a different constant. Call it P, capital P for particular. How about this one? What's the second derivative of a constant? 0. Okay. And then it would be 4 times P, right? Minus 4 times P. Doesn't work? Why not? Oh, yeah, okay. Normally we've been talking about like theta as a like an actual thing that we're tracking for motion, but here really we should call it like alpha or something, like some kind of it's one angle. So in this case it is like some kind of constant value. Yeah, so here we could say that P is G sine theta over 4. And then it works. And really, like even advanced differential equations, if you're not sure, like you can start off by just guessing 0. 0 is usually works, but it's the boring solution. Like in this first one, we could have said x equals 0, and then technically it works for all time, but that would mean like nothing changed and we had no initial condition. So it's boring. But then in this case, we could have said like, okay, let's try x. Well, x only works if there's an x squared, which only works if there's an x cubed, which only works, and you would add all these terms, then you end up with an infinite series, which turns into sine and cosine. For funsies, if you're like, guys, let's do infinite series this Saturday afternoon, infinite series Saturday. All right, so our final solution, x of t, well, not final, but pretty close to the final, is a cosine 2t plus, did I call it sine? I think a sine. B cosine 2t plus g sine theta over 4. How do I take care of a and b? Because those are still just unknown constants. We use the initial conditions. So one thing that it took me a while to appreciate this is that even though I'm kind of guessing, this whole time I've been guessing and checking my differential equations, but in those guesses, I introduced integration constants in the same way, like the integral of x is x squared over 2 plus a constant. I did the same thing here of like, I took two integrals, so I have two integration constants. I'm going to solve for those now with mind bullets. So x of 0, what did we call it? 1, 2, 10? 1 is 1 meter. X dot of 0 is 2 meters per second. What's the sine of 2 times 0? 0. What's cosine of 2 times 0? 1. What is, and then we'll take one derivative, so then we end up with like a 2a cosine 2 times 0. What's cosine 2 times 0? Well, I guess we already did that. You already answered it. Minus 2b sine 2 times 0. And then what's derivative of our constant function g sine theta over 4? 0. Cool. So my first, I'm looking at this, if I call this like equation 1, equation, let's call it little I, little double I, 1 and 2. So in this second equation, the only non-zero terms are the 2, my initial condition, and 2a. So I can say a is 1. Looking good? So now I can say 1 meter is, well, the 1 is kind of gone, but b times 1 plus g sine theta over 4. So b is going to be that 1 minus g sine theta over 4. Sorry, Shelley, I missed the question. There was XH. How did we know? Oh, how did we know that omega squared, that negative omega squared came about? I think up here. That one, yeah, that was a little while ago, but we knew that because if we have sines and cosines, as you take two derivatives, whatever that frequency is inside, it's at negative omega squared times the sine and negative omega squared times cosine. Like you end up back where you started, but negative. Now we have our final solution, because we know that it's 1 times sine 2t plus 1 minus g sine theta over 4 cosine 2t plus g sine theta over 4. And I plugged in some numbers just so we're not dealing with like, mostly I just wanted to do that so we didn't have discussions about like which ones do we know, what do we not know. But here, this one is our d0 over omega, like our natural frequency. That's our like initial position, that x0, because it was 1 meter. And that's our like g sine theta over omega squared. And we got those from that particular function. How are we doing? Oh, and we're right at time. Beautiful. And the sun's coming out. It's like it all worked out. Maybe a rainbow. Yeah, we just had to do some differential equations. But anyway, that was our speed run through the second order differential equations. Then we'll be back on Wednesday to build quiz number 3. That's the plan for Wednesday. Cool. Thanks a lot. 20? Yeah, 20.